Friday, you guys were working on this elevator lab where you got in an elevator, collected data, and forced data for as the elevator was moving up and as the elevator was moving down. And it can be a little bit tricky to read, and there's a few problems on here I want you guys to do. So I'm going to go through this a little bit with you guys. The background here, I think everybody did okay on. Okay, you get on an elevator on the ground floor and it's moving up. Which way does the elevator accelerate when it starts to move? Well, if you're going from rest to moving and you're going up, then it accelerates up. And if it's accelerating up, then the force is up. And if the force is up, you're going to feel heavier. And if you think about it, it makes sense because I'm going to draw a little picture over here that sort of depicts all the little forces. So you're standing on the floor. Here's a person standing on the floor. And generally, when you're standing on the floor, there's the force due to gravity, which you don't really feel, right? And then there's the other force that you do feel. This is called the normal force. This is the force the floor exerts on you up to keep you from falling through the floor. And this is the one that we actually feel, right? When we fall and hit the floor, we feel the floor pushing back. When we take a step down onto the floor, we feel the floor pushing back. Okay. Well, if all of a sudden we're going to start to accelerate up, what we feel is this force get bigger. So we feel like we weigh more, even though gravity doesn't pull on us harder. The floor has to exert some extra force to get us to move. Okay, and then we repeat the process coming back down. Oh wait, I guess number 2 says, what about when the elevator comes to a stop? Which direction is the force during this time? Well, you've been moving up at a constant speed, and all of a sudden you've got to slow down and stop, which means you have to accelerate down, which means the force also has to be down. But if we come back to the same picture, that means the normal force then is actually going to get a little bit smaller. Instead of supporting all of your weight, it's just going to support some of it so that you slow down and stop. So you'll feel lighter. Okay? 3 and 4 say, hey, let's say we're going the other way. Now we're on the top floor and we're coming back down. Which way does the elevator accelerate when it starts to move? Well, it's going to accelerate down, which means the force has to be down, which means, again, you'll feel lighter. Same reason. The normal force is still there. It's still pushing up, okay? But it's not pushing up as much as it used to be because you actually need to accelerate down. So the force due to gravity needs to feel bigger or be bigger than the normal force pushing up on you, okay? And then again, which way will the elevator accelerate as it comes to a stop? Well, the elevator's moving down, which means it needs to accelerate up in order to stop, and that means the force has to be up, and you'll feel heavier. Okay? And I think when you went through and did that, that was the data that you saw. Okay? And so here's the procedure, and it said, okay, let's go ahead and sketch the graphs that we got. Now I'm going to show you some graphs that I got, and then we're going to see exactly how to interpret those. So on my iPad, I need to launch the Graphical Analysis app. Okay, and from here, I've got the data loaded. Now, if yours isn't loaded from Friday, okay, down at the bottom right of your screen, there is this little clock, and if you touch that, it shows you all the data that you've ever collected unless you've gone through and deleted those. You can delete them. It's just like deleting an app. Push and hold on it until it wiggles and push the little X. Okay, and so October 12th was the day we collected data, so I'm going to push the October 12th graph, and that's the one I have. Now you guys collected multiple runs of data, and they're all stored, so up in the top left is this little, I don't know, the 3 lines, the bolded graph. Okay, if you touch that, you can find different runs. So right now I'm looking at run 1, which is actually a little bit goofy because it's not the run that you think it is. Okay, we thought it was the one moving up, but if I take a look at this, in this area of the graph, right here, okay, you can see that there's 0 force. That's because nobody's standing on the force plate. And then we have all these wiggles. Well, this is like left foot, right foot. Okay, so we step up onto the force plate, and then it's fairly constant here, and then the button gets pushed, the elevator starts to move, and you'll see my force actually drops a little bit. Okay, the force comes down, and then it moves at a fairly constant force, or the force that's exerted is fairly constant, and then I get this upward force, and then the force is fairly constant, and then I get a little bit of a wiggle at an end. Okay. Well, what I want to do with this force is, or this force time graph, is analyze it, but I also kind of want to sketch it on my paper, and I'm not worried about all this noise over here. So when I go to sketch this graph, I'm going to simplify it a little bit. So back on my lab sheet, I'm going to sketch this graph, okay? And it did start at 0, and then it came up, and there was some wiggles, so I'll put some wiggles, but mostly stayed fairly constant. And then we had this sort of downward thing, and then fairly constant, and then this sort of upward thing, and then fairly constant. Okay? So, and over here I have force, over here I have time, and yeah, it was a little bit goofier than this, but I get the basic idea. But wait a minute, I gotta analyze my data on this one. What can I see about this force right here? Well, the person stepped on, but then right here in this time interval I get a little bit of a less of a force, which means the elevator is accelerating down. And if I start with an acceleration down, I can't be on the way up. Okay? So I actually have this one drawn backwards. It's not what I thought I was looking at. So I can't put it here. Okay? It must be on the way down. So over here on the right, I'm going to redraw my graph. Okay? It was here, jumps up when the person steps on it, then I get this little spike down, then it stays fairly constant, then I get this spike up, then it stays fairly constant. Alright, so now I have my graph. And I'm pretty confident I got the right one in the right spot, because I can see, okay, person, it's at 0, person steps on it, and then we get this wiggle down, and that means that the force is actually a little bit less. I'm going to feel a little bit lighter, which must mean the acceleration is down, and so the elevator must be moving down since this is the initial acceleration. Then I get this acceleration up. That doesn't mean the elevator is moving up. Okay? That means is I'm slowing down from where I used to be. Okay, so here's my graph on the way down. Similarly, I can sketch my graph on the way up. I could go look at my data, but I have a pretty good idea what it's looked like. Okay, it's going to start down here at 0 just like the other one, and somebody's going to step on it, and it'll be all probably spiky and wiggly, but then I should get kind of a bump up, right, and then sort of a bump down, and let's see what that means. Okay, here we've got 0 force, nobody stands on it, they step onto it, there'll be some spikes and wiggles. Okay, elevator starts to move up, so we need an acceleration up, so we need a force up, so the force gets a little bit bigger. Elevator moves at a fairly constant speed, so all we have here is the force that exerts just to hold you, and then the elevator slows down, and so we get this negative acceleration, so negative force, and then elevator stops. And there's usually a wiggle at the end when the doors open. Okay, it says using your graph we're supposed to determine the mass of the person. To do that, we're going to actually need to pull some information off the data you collected. So if we go back to that graph, we have in this area right here, we have a fairly constant force, and so that's where I'm going to click anywhere in that, and it says that's about 673 newtons, okay, which means I can figure out the person's mass. So I'm going to label on my force time graph over here, I'm going to label that this is about 673 newtons. Why is that 673 newtons? Well, it takes 673 newtons of force just to hold the person still. So if I want to calculate the mass of the person, I'm going to say, okay, well, let's start with the free body diagram. Person was standing on the force plate. Okay, here they are. There's two forces. We're either not moving or moving at a constant velocity. So I can say the acceleration is 0, and if the acceleration is 0, then net force needs to be 0. Okay, and so I know gravity is pulling down, Fg, and I also know that the normal force, or the force from the scale, is pushing up, Fn, and so I can say Fn plus Fg equals 0, which means I can say Fn equals negative Fg. Okay? But I know that Fg is equal to mass times the acceleration due to gravity, so this is equal to negative m times g. Okay. Well, I know the normal force. That was measured. That was my 673 newtons. So now I have 673 newtons is equal to negative m times negative 9.8. It's negative because I picked up to be positive. Okay, so I take 673 divided by 9.8 because those two negatives cancel, and I'm going to end up with the mass of the person. And if I do that real quick, I get 68.7 kilograms. Okay? So the mass of the person equals 68.7 kg. Mine's kind of messy, but you get the idea, right? We're just going to take whatever this mass is here and divide it by 9.8. Okay. Alright, it says, okay, so from there I want to know the acceleration of the elevator as it begins to move up, which means I'm really kind of interested in this thing right here, this little bump at the beginning of my graph. Okay. Well, I actually need to find how big that bump is, so I've got to go back to my data on the iPad. So let me grab that. Now this graph looks a little bit messier because I'm actually showing two data runs at once, right? The green line, which we looked at earlier, was the way down. This orange line is actually the way up. But there's no beginning to it, right? Data collection didn't get started until a little bit after we got on the force plate. But that doesn't mean this data is not usable. Okay, I just got to pay attention to what's going on. You can see on, let me move this thing out of the way. Okay, you can see on the green line there, this fairly constant area here, that's where the elevator's moving at a fairly constant rate. The person is just standing there, and it matches up with this fairly constant orange spot right here. That's because it's the same person, we have a similar mass. Okay? You can see right here on this orange line there's this downward spike. That's where the acceleration is down, so this is the trip on the way up, this is the when it comes to a stop. Okay? Over here at the beginning of the graph, okay, you can have, it's a little bit tricky to see, but there's this spot where the elevator just starts to move, and it's right here, and you can tell because we get this spike up in force, and then it gradually comes back down as the elevator reaches speed. So what we kind of want to know about that is how big that force is. And so again, I'm just going to touch on it somewhere in there, and I'm not going to pick the biggest spike, and I'm not going to pick the lowest spot. I'm going to pick somewhere in between, and so I can see right there that's 689 newtons. Okay, so there's 689 newtons of force right there making the elevator accelerate. The elevator and the person. We're just measuring the forces on the person. Okay, so 689 is a number I'm going to need. So if we come back to this graph over here, I actually now have a value for this upper limit of force, and I'm going to call that, that's my 689 newtons that I just measured. So I want to know, okay, so how fast was the elevator accelerating, or what was the acceleration on the way up? And so I can say, okay, net force equals mass times acceleration. Okay? And I know the net force because I know how big the normal force is right here, and I know the force due to gravity, which is actually the 673 newtons from before. So we can say this is 689, that's the normal force pushing up, minus the 673, that's the force of gravity pulling down, we could do a plus and negative, is equal to mass. Well, we just calculated the mass. Since this is the mass of the person, this is 68.7 times their acceleration, a, okay, and so we can find the acceleration of the person, which is also the elevator, since that's what they're riding in. So if we do this, we have 689 minus 673, which is what, 16 newtons. So I have 16. Let me get rid of this. I have 16 equals 68.7 times a, and then all we have to do is some division, and we're going to get the acceleration of the person, which is also the acceleration of the elevator. So 68.7, 16 divided by 68.7 equals 0.233, essentially. A equals 0.233 meters per second per second. Okay? That's not a very big acceleration, but we don't expect it to be. We can feel it, but it's not like we're skyrocketing to the top of this thing. Okay? Then we're supposed to repeat the process for the elevator as it comes to a rest moving up. So then I'm going to look at this section of my graph. I'm going to say, okay, what was the force there? So if I grab my graph and I bring that in, then what we can see is, okay, so this is that downward wiggle on the orange graph right there at the bottom. How big is that force? So if I touch, again, somewhere in the middle of that so that I can see, you know, the force, the average force somewhere in between, that force looks to be 626 newtons. So I'm going to use that number now. Okay? So on my graph, I know a lower limit, and I'm going to go ahead and use blue for this. Down here, this is like 626 newtons. And I'm going to repeat the process. Net force equals mass times acceleration. So our net force, which is the sum of the forces acting, we have 626 newtons acting up, that's the normal force that's getting measured right here, minus the 673 newtons, which is the force due to gravity pulling down, equals mass 68.7 times acceleration. Okay, and so now we get negative 47 equals 68.7 A. And if we do that math, 47 divided by 68.7 equals negative 0.68. Okay? So our acceleration is negative 0.68 meters per second per second. Okay? They're not exactly the same. Is that okay? Sure, it's okay. It just means the elevator might come to a rest more abruptly than it starts out. Okay? And I'm gonna have you do a little bit more with this. Which motions resulted in less force acting on you? Why? Okay, go back, look at your graphs, okay, and see why less force acted. Okay. Can we determine the constant velocity of the elevator as it moved up? If so, find it. If not, explain why. If the force of motion, okay, so there's some questions I want you to answer here. You actually can find this, okay, because you're going to be able to find an acceleration, and you're also going to have a time interval. Okay, let me show you that. Okay. If we bring in this graph one last time, okay, and I only want to see one at a time. And it doesn't matter which one I pick, but I think it said moving up at a constant speed. So I'm just going to take a look at the orange graph. Okay, and you can see it auto scales, and so this is really kind of hard to see all of a sudden. Well, okay, maybe not. Okay, so let's take a look at what it is. This little wiggle right here, this is stepping on, stepping off. It's right after the person steps on. Okay, but this big spike in this area right here, this is where the elevator starts to accelerate up. Then we get this fairly constant force. This is where it's moving at a constant speed. And so the question says, can we figure out how fast this constant speed is? And we actually can, because if we take a look at this time interval from here to here about, okay, that's where the elevator starts to accelerate and move up. Okay, and if we look at that, we can find the average acceleration. So I'm going to turn on statistics, okay, and it tells me the change in x, which is the time, right? So right here I'm looking at the time, and also the mean value, which is right here. So it's got a mean value of 684 newtons, and it's got a time of 1.44 seconds. Okay, now what I'm really interested in is the time. Okay, the mean value we kind of already got. We estimated it off the graph before. Okay, but this change in time, this 1.44 seconds, that's pretty handy. Okay, because what we can do with that is we can say, okay, yeah, if I want to know the final velocity of this elevator, I want to know v. That's what I'm looking for. Okay, I know v is equal to v naught plus at. And I know what the elevator started at, right? The initial velocity of this elevator was 0. From before, if we go back and look at our data from before, we said, okay, the acceleration there was about 680, or not the acceleration, sorry, that was a force. The acceleration up was about 0.233 meters per second per second. Okay, so over here I can go ahead and I can record that number, 0.233 meters per second. And now that we got time from our graph, our t was 1.44 seconds, we can actually figure out how fast this thing was going. So v equals v naught plus at. I guess I'm going to write it twice. And so this equals 0 plus 0.233 times 1.44. And I don't know why it's getting so messy, but whatever. And so you can see that this is going to be about 0.335. Okay, so I can't do math. Equals 0.335 meters per second. So it takes a while. It's not moving very fast, but it gets us from one floor to another. Okay, and then answer the rest of these questions, and I will take this lab. If you have any questions, let me know.